Okay, so we're going to be recording this part of the session where we're talking about electrical potential. So let's say this. Let's say that we have an electrical field. We have an electrical field here. And the electrical field has that direction. This is an electrical field. Okay. The electrical field is being generated by some sort of charged object or object. So we might have a combination of negative and positive charges here. If the electrical field is going outwards, then I can probably infer that the whole electrical field is probably have more positive than charges than negative charges. But we've got an electrical field here. Let's assume that we've got just positive charges here, and we've got an electrical field that's being generated. Okay. Now, again, I'm going to give the definition again of voltage or electrical potential. I'm going to place myself somewhere here. I'm going to place myself here. This point that I'm drawing in green, I'm going to call that point A. It's a point in space where the electrical field is. Okay. And so I'm going to take a positive electrical charge that is located in infinity. So it's really far away. And I'm grabbing that electrical charge and I am going to be moving it towards the electrical field until I reach the point A. Voltage or electrical potential, let me see what color I'm going to use here. The voltage or electrical potential is the energy per unit charge, or the potential energy to move that charge from infinite towards that point A. Okay. Now, why is this important? Let's see. Let's see. I'm going to choose somebody, and we're going to do the. Let's see what we're doing, and we have to turn on our cameras. Let's see. Rene. Going once. Rene going twice. Remember that this is being recorded. Rene going. There we go. Perfect. Okay. Yeah, we have to have the cap ready. Okay, Rene. Let's say this. Remember that the electrical field is this invisible energy that's emanating from a charged object. And if this is a positive charge, am I going against or am I going in favor of the energy when I'm trying to move it in the direction of the orange arrows? Am I going against it or in the same direction as it?
You're going against it, no?
Yeah, and remember that we talked about that positive charges, they're repelling each other. So, Rene, imagine that you're this positive charge, okay? You are this positive charge. Give me a moment. Mess this up here. Okay. This is Rene, and Rene is the positive charge. And Rene has a cap. and you're that positive charge. And imagine that the electrical field is kind of like a river, okay? You're in that river, and you're going against the river. So you're moving, you're walking against the river, okay? But this is a very weird kind of river. It's a river that the closer you get to this part here, because of what we've talked about, you remember, Rene, that the electrical field is larger the closer we are to the charge, right? The further we are, it's less. So what's going to happen, Rene, when you start getting closer to this point A?
Like the current or the resistance is going to be stronger.
Correct. Perfect. So when you're in infinite, you're not feeling the electrical field. And then you start getting closer, closer, closer until you get to this point. And when you get to this point and stop, you're going to start feeling the electrical field. Okay? We okay up to that point? Now, I just said something. You're walking against the river, Rene, and then you stop. And you have to stay there. So imagine that the river is really strong. What's going to happen, or how are you going to feel if you want to stay at that position?
Well, you have to like plant yourself in that position because you're going to have a lot of current like going against you.
Yeah. So if you want to stay in that position A, there's going to be a certain energy that you need to stay in that position. Would you agree with that?
Yes.
Okay. Now, Rene, imagine that you are further away. Let's say that you are here. I'm going to put 3 points here. And again, imagine, Rene, that you're in a river. And let's make this even more dramatic. You're in a river and you're carrying the most important thing in your life in that river, and you do not want to fall in that river. So you just told me that in point A, you need a certain energy to maintain yourself there because the river is at a certain strength here. In point B, are you going to need more energy or less energy to stay in that position?
You're going to need less energy in point B.
Correct. Why? Because you're further away. And since you're further away, the electrical field or the river is less strong. And what about point C?
You're going to need much more because you're closer to the start of the field.
Correct. So are we okay up to that point? That's what voltage means. Voltage is the electrical potential. When we're in an electrical field, if I'm located in point A, B, C, what's the energy that I need to be able to maintain a charge there? Okay. And why is voltage important? And with this, give me one more minute and we'll go to break. I'm going to put VA, VB, and VC. If I want to go from point B to point A, I need a certain amount of energy. If I want to go to point A to point C, I need, or from point B to point C, I need more energy. But what would happen if I want to go the other way around? Now, Rene, I'm going to ask the other question. Now you're moving in this direction. What's happening there? If you're going from point C to point A to point B?
Well, you're going to go much faster because the current is going to help you move.
The current is helping me out. Okay. So if I'm moving in one direction of the electrical field, I need a certain amount of energy. If I'm moving in the other direction, the electrical field is helping me out. Okay. And basically that's the principle. That's why this is called voltage. Voltage is that measure of energy that I need to be able to move one charge from one point to another. And moving charges is called current. And so that's why there's a very important relationship between voltage and current. And current is what we use to basically power up everything that we need to power up. Okay. Thank you, Brennan. We're gonna pause for a 10-minute break, and we'll continue with this. Okay, so we're talking then about electrical potential, and so the electrical potential is going to be that energy that's required, that It's going to be that reference of the energy that we would need to have a point charge located at some point in an electrical field. And so this is related to the work that's going to be needed eventually to be able to move a charge from one point to another. Shorter definition of electrical potential is that it's the total potential energy per unit charge that is going to be needed or located at a certain point in space. And obviously this is due to an electrical field. If there's no electrical field, there's no electrical potential. So if we are, let me switch over here. If we're talking about two charges that are of the same value, if we try to bring these two together, it's going to be difficult because they're going to repel each other because of the electrical fields, because the electrical fields are going to be going against. Okay. And so, again, going back to the analogy of the river, and when Rene was in the river, and okay, if I stay at one point and go forward against the river, I'm going to need more energy. It's the same thing happening. If the two charges are the same, the charge there, I need energy to be able to bring them together or to maintain them in the same position because they're going to be repelling each other. However, if I have charges that are opposing signs, if I have a positive charge here and I've got a negative charge here, then we've already seen that the electrical fields are going to, this one is going to be going out and the other one is going to be going in. So we already saw that something like this is happening. And so this is what we reflected upon, that's the attraction. So if I have a positive and negative or charges that have different signs, then actually it's going to be easier to move one from one point to the other because there's going to be an attraction. If I try to separate them, that's where the problem occurs, that I need more energy. And so this is reflected in this concept of potential. So basically, what happens with a battery? Batteries or any sort of object that is or any sort of thing that stores electrical energy is going to generate a difference in potential. Okay, it's going to generate a difference in potential. Okay, and so what is going to be that difference in potential? It's going to be that energy that can help me move a charge from one point to the other. So basically, when I have a battery, I have two extremes of that battery that have different potentials. One is a positive potential and one is a negative potential. So once I connect these two via some sort of object or some sort of connection, then the charges are always going to go from one potential to the other, or they're going to go from the place that has the largest potential to the place that has the less potential. And that's how electrical charge is moved from one place to another and generating what we know as, or what we call, what we call current or electrical current. Okay, which is basically this that we have here. This is electrical current. And right now we're in electrostatic, so we haven't talked very much about electrical current. We're going to do that in the electrical circuits unit. But it's important to note that this difference in potential, which is basically what we were talking about in the different points in the river analogy, is this this reference that's going to say, okay, to move a charge from one point to the other, I need this amount of energy. Okay, and so voltage, that's what we call voltage. Okay, the units of potential energy are volts. So it's usually denoted by a V, And usually sometimes energy is also denoted by a U, but the most common is V, which represents voltage. Voltage is the energy per charge. So it's basically joules divided by Coulomb. Okay, so any place or anything that has a voltage, the voltage is a reference of the work that can be done to move one charge from one point to another. And so a high voltage means that there's a lot of energy there to be able to move charges. So if you see something that says danger high voltage, well, that means that that device or that whatever grid or you're looking at has a lot of potential or a lot of energy to be able to move charges from one place to another. So if there's something that has high voltage and suddenly you are the medium that's here in the middle that's going to connect things, well, all of the current, which is a very high current, is going to go through you, and well, that's not going to be good for you or for anybody. Something very important with voltage is that voltage is a scalar, okay? Now, what is the difference between or why is it important for us to mention that it is a scalar rather than a vector? What's interesting or important there? So it's not a vectorial, it's not a vector, it's a scalar. What's important there, or what's relevant in that? What's the difference between something that's a vector or vectorial and something that's scalar?
Vectorial charge, for example, has a direction in a unit, I think. And I think that a scalar one just only has like the unit itself.
Yes, correct. Unit. Correct. And what you mean by unit is the magnitude. So in a vectorial.
Yeah, the magnitude.
In something vectorial like a force is vectorial. So a force has a direction and a magnitude. The electrical fields are vectorial. They have a direction and a magnitude. Voltage doesn't have, or energy doesn't have a direction. It only has a magnitude. So I'm only interested in the magnitude of the potential in this case. So voltage is a scalar. It doesn't, we're really not interested. The voltage doesn't have a direction. Okay, it just has a magnitude. And that actually helps out in the calculations. It's going to help out in the calculations eventually. And so this is what we've been talking about. Oh, so this is being recorded. So I'm yawning just because, again, our dogs have been coughing a lot, so we haven't been sleeping. So this is being recorded. So it is under record that my classes are so boring that even I'm yawning in my own classes. So for the record, that is happening. This is what we've been talking about throughout the course. So positive charges attract each other. Positive charges or charges of the same value repel each other. Charges of different values or of different signs are going to attract each other. And these charges generate electrical fields that are going to contribute to affect any charge that is in that electrical field. And now when we're talking about potential, one analogy that we can make is that imagine that we have two bars that are oppositely charged. And so if we want to maintain them in the same position, there's going to be a certain energy for that because the bars are going to try to connect to each other. If the bars were of the same sign, then if the bars were of the same sign, then there would be a certain energy to try to put them together because they are trying to repel each other. I'm sorry, I muted it. I'm sorry. So this is the example we were giving. In the case of the relationship, I'm going to say again, we're mentioning that this is the Leonardo theorem of controversy between Newton and Coulomb. Basically, we've got gravitational potential energy. The gravitational potential energy increases while we get further from, in this case, the Earth. And the gravitational potential energy is going to be given by gravity. So the farther we are, the more potential energy we have. The potential energy, in the case of electrical, there's many combinations because it depends on the signs of the charges. And so depending on if the charges are positive or negative, if they're going to increase or not. If the electrical potential is going to increase or decrease. So in the river analogy that we were talking about, if we have a positive electrical field because of a positive charge with an electrical field regarding another positive charge, the further away we are, then the electrical potential decreases. But if we are talking about two charges that are of the same sign, the more closer we get, or the further we get, the electrical field is going to increase. And so remember that the difference between gravitational energy and electrical energy, or gravitational fields and electrical fields, is that electrical fields are always going to have these variants according to the combinations of the signs we're talking about. And so imagine that we have, again, a bar and we have an imaginary charge, and we're trying to move that charge within this electrical field. The electrical field is going to help me. And so the potential is a potential that's going to contribute to the movement towards the bar. And it's going to be contributing to that. If we have a positive bar and a positive charge, then the electrical field energy is going to be a repulsion, or energy regarding to the propulsion. So if we have positive and negative, it's less energy that I need and more energy in the outer. And if I have positive and positive, there's more energy at the beginning and less at the outwards. And the river analogy that we were given kind of demonstrates that. It's like going against or going in favor of the current. And so the electrical potential of different types of objects is similar to when we were talking about electrical fields regarding different types of objects. It's going to behave differently depending on the type of object. So the first type of object that we're going to see here is the typical point charge. So what is the electrical potential of a point charge, or what is the voltage at a given point? The voltage is simply going to be the K, which is our electrical constant, multiplied by the charge divided by the distance, where V is the electrical potential energy or voltage, Q is the point charge, R is the distance to the point where we're analyzing the potential, and K is the electrical constant that we have. And so, for example, if we were to calculate the difference between the potential at R equals 5 and R equals 10 for a single point charge of one coulomb located at the origin. So let's assume that we've got a charge here. We're going to say that this is positive. And then we've got two distances here. We've got one distance that's one distance here that I'm going to call this point A. And this distance is 5 centimeters. And then we've got another distance, or another point over here that we're going to call point B. And this distance here is 10 centimeters. Okay. The total distance there is 10 centimeters. Okay, just to be clear, this distance here is 10. And this distance here is 5. And we want to know the difference of potential between those 2 points. So let's calculate the potential for each of those points. So for the first point, the potential or the voltage for point A is going to be equal to K, which is the electrical constant, multiplied by Q, divided by RA, which is the distance in A. And this would be, K is 9 times 10 to the 9. Q is 1 coulomb. And RA is 5 centimeters. So this would be 0.05. Can somebody help me out with that calculation, please?
I got 1.8 times 10 to the 11th.
Okay. 1.8 times 10 to the 11.
Yeah,
Thank you, Lucia.
you're welcome.
Okay, and these are volts. Okay, these are volts. Please, when we're doing calculations, let's verify this. So the rest of you also do the calculation so we can verify. Now, what is the potential in point B? The potential in point B is going to be K, Q, R, B. And this is going to be 9 times 10 to the 9 multiplied by 1 coulomb divided by 0.1. Can somebody help me out with that calculation?
I got 9 times 10 to the 10.
9 times 10
To the 10
to the 10
volts. Yes.
volts. Okay, perfect. Okay, let me just check something here. Okay, and so we've got those two those two potentials there. Now, which of the two is larger? Can somebody tell me? That's just looking at the numbers, kids. Which of is VA larger than VB? The VA is larger. Is that clear to everybody?
Yes.
And VB is smaller. Remember the Rene in the river holding something very, very important analogy. The charge is generating an electrical field. And remember that the reference is always going to be a positive charge. So the potential in B is going to be smaller than the potential in A. And remember the analogy, we're going against the river. So staying at a point that's closer to the charge is going to require more energy than staying at a point that is further from the charge, okay? And so it's asking us to calculate the potential difference between those 2 points. So the potential difference, which we're going to call VAB, is going to be the difference between VA minus VB. Can somebody tell me that, calculate that difference, please? Okay, can somebody do that calculation, please? 1.8 minus times 10 to the 11 minus 9 times 10 to the 10.
I'm doing it, Professor. Wait a second.
I got, wait, 9 times 10 to the 10. Oh, well, yes, because it's the half, no?
So you
Yes,
guys
yes.
did it 9 times 10 to the 10.
Yes, me too.
Yes.
Mhm. That would be the voltage difference between those 2 points. What is the voltage difference? That's the difference in energy between being in one point and the other, or the energy it would be. Another way of interpreting this is it's the energy that would be required to go from point A to point B. Okay. And it's a positive energy because we're moving in the same in the same direction as the field. Okay. Questions with this one? Okay. Now, what happens if we have more than one charge in the space? So right now we're just looking at one charge. What if we have multiple? Sorry. What if we have multiple charges? And so if we have multiple charges, sorry about that sneeze. If we have multiple charges, then these charges are going to all contribute to the potential in the point we're analyzing. However, this is interesting because the reference that we're going to have is that, remember that the reference is always going to be a positive charge. Okay. The reference is always going to be a positive charge coming to infinity to that point. So if we have positive charges, the positive charges are going to contribute a positive potential, and the negative charges are going to contribute a negative potential. So since these are scalars, it's literally it's literally an arithmetic operation, with the positives having a positive sign, the negatives having a negative sign. Or in other words, the positive charges are going to contribute a positive potential. We're going to contribute the energy, and the negative charges are going to take that away. Okay. And so let's look at an example of that. So it says, find the electrical potential at the center of an equilateral triangle whose side is 1 meter, and there are 3 positive charges of 1 coulomb, 2 coulomb, and 3 coulombs in its corners. Okay, so we've got an equilateral triangle. Okay, and in this equilateral triangle, we've got 3 positive charges, 1, 2, and 3. This is positive, positive, and positive. And let's call this one 1, 2, and 3. The distance here in each of the sides is 1 meter. Okay, and 1 meter. And they're asking us to find the electrical potential at a point located exactly in the center of the triangle. Okay, so the point we're talking about is right here. Okay, we want to find the electrical potential in this point that I'm going to call A. Okay, so actually VA, since all of the charges are positive, is literally going to be the sum of V1 plus V2 plus V3. If any of these charges were negative, then instead of putting a plus, we would have put a negative. And what we need to find here, basically, to solve the problem, we need this distance here that I'm going to call R. And I think you will agree, or you should agree, that R is exactly the same distance that we're going to have here. And it's also the same distance that we're going to have here. Okay? It's going to be the same distance we've got in those points. Okay? Okay, how could we calculate that? How could we calculate that point? Let's see, trigonometry 101. Anybody?
Well, if they're all the same length, shouldn't they all have the same angle? But I don't know if that angle matters. I have to find the distance from the point to the middle, Professor. That's what you're asking.
Yep, and basically what we've got here, if you notice, is I'm going to take well, first of all, does everybody agree that this distance, we need the distance from each of the charges to the middle? But I hope you all notice and agree that this distance here is the same one as distance and the same one as this one. So we just need to find one of them. So I can do this. I can look at this triangle here. Okay. And I'm going to bring this triangle over here as a zoom. Okay. If you hear my daughter, I don't know if you hear my daughter in the background, but on Fridays, it's the catechism class. And since it's the only class that's in Spanish, she really gets excited participating in that class, which is fun, but she doesn't let anybody else participate. Would you, all of you, agree that this distance here is 0.5? Okay.
Yes.
We don't know this distance over here. We could find it. I'm just going to call it X, but we need to find R. Can somebody, does somebody know what this angle is here? Can somebody tell me? Trigonometry, kids. What is this angle here? What's the value of this angle here?
60, 30,
60.
30.
I want to say 30.
Yeah, 30.
Because
Okay.
the
Yeah.
whole angle is 60 because it's equilateral, right?
Yes, correct.
But it's half. I don't know if it's half, but I would guess 30.
Yeah, 30. I think it's 30.
It's 30. It's 30 because correct. What you're saying, JC, the whole angle is 60 degrees, and we're basically splitting it in two. So this angle here is 30 degrees. Okay. So we know that theta is equal to 30 degrees. Okay. And so if I have those three, then I can calculate the value of R using the trigonometrical function. So I've got this side here, which is 0.5, and this would be the cosine. So the cosine of 30 degrees, it would be equal to 0.5 divided by R. Okay, so the cosine of 30 degrees would be 0.5 divided by divided by R. So that would mean that R would be equal to 0.5 divided by the cosine of 30 degrees. Okay. Can somebody help us out with this calculation, please? So somebody give us that value.
It's
While
0.577.
0.577. Remember to have your calculator in degrees. Okay. 0.57. I'm going to say 0.57. And so V1 is going to be equal to K Q1 divided by R. And this is going to be equal to, I'm not going to write down the whole K. You know that K equals 9 times 10 to the 9 multiplied by 1 column divided by 0.57. V2 is going to be exactly the same thing, but it's going to be, instead of having Q1, it's going to be Q2. And Q2 is 2 columns divided by 0.57. And V3 is going to be exactly the same thing, K Q3 divided by R. But Q3 is equal to 3 columns. So please calculate those through those 3 values. So what's the value of V1, please? V1, V2, and V3, please.
I got that V1 was 1.56 times 10 to the 10. And then I haven't calculated V3, but I calculated V2, and it was,
Okay, and V2, go ahead.
it was 3.12
3.12, okay.
times 10 to the 10. And let me calculate V3 right now. And V3 is 4.68 times 10 to the 10.
4.68 times 10 to the 10 volts. Okay, and the sum of these 3 is going to be the total potential voltage. So can you guys give me the sum, please? Which is adding these 3. V1 plus V2 plus V3. It would be, they're all times 10 to the 10. Can somebody please do the calculation?
9.35 times 10 to the 10.
9.35 times 10 to the 10 volts. Okay. Okay, and that would be the total potential that is being affected or that would occur in that middle point of the triangle. Meaning that if I wanted to move a charge and locate it at that point inside the triangle, due to those 3 charges, the energy I would need per unit charge to do that would be 9.35 times 10 to the 10 volts. It's a lot of energy to move the charge to that point, okay? If in this problem, any of the charges were of a different sign, okay, let me just save this. Let's say that instead of being 1 column, 2 columns, and 3 columns, we had 1 column that was positive, the 2 columns that were negative, I'm sorry, and 3 columns that were positive. The only thing that would change here in the triangle would be that charge 2 would be negative. And what would happen with the calculations? Well, remember, the positive charges are going to contribute. The negative charges are going to contribute to the potential energy. The negative charges are going to detract from the potential energy. So what would happen here is that the three calculations would be exactly the same. Okay, the three calculations would be exactly the same. The only difference would be that in the case of the charge 2, in the case of charge 2 would contribute negatively to the, this would be negative, okay? It would contribute negatively to the overall voltage. And so for this other version, we would add these two and we would subtract the V2. Can somebody do that calculation, please? And just so we can see the difference.
If the two would have been negative.
Yes.
It would be 3.09 times 10 to the 10.
3.09 times 10 to the 10. And notice that it's less than the other one. Okay? And so just remember the electric field hockey. You guys did that. If you had a lot of positive charges, they were helping move in a certain direction. But what happened when you put a negative charge? The dynamic changed, and instead of pushing it, pulled it toward someplace else. So it's similar here. When we have the three positive charges, the three positive charges are going to be adding to a potential energy that I need to move the charge to that point. Meaning, if I have a triangle with three positive charges and I want to put a charge in the middle that's positive, I'm going to have, how much did we have it? I think it was 9 times 10 to the 10 volts. That's the energy per unit charge that I need to put a charge in that position of the triangle. But if I remove one of the positive charges and I put a negative charge there, the negative charge is kind of helping me out. So instead of needing so much energy to put the charge in the middle, I need a little less energy because the negative charge is contributing. And again, you saw that in the electrical field hockey. If you would have put all positive charges, there was certain dynamic, but if you added negative charges, those changed the effects of the overall electrical field and made the ball move to a different position. Okay, and so the same thing happens. The positive charges are going to contribute. The negative charges are going to detract from the potential. Okay. Okay. Questions with this one before we kind of wrap up. This is going to be recorded, and I'm going to upload it to Blackboard. And these solutions to these two problems, I'm going to put my ugly writing, but there's also a normal solutions without my ugly writing that's going to be there also for your reference. Okay. Okay. Questions?
No.
Okay.
Mm,
Let
questions?
me. Okay.